First one, sir, I'm going through the second experiment, sir.
Okay. What about others? So, so in TDM digital scheme, time division multiplexing, the concept of time division multiplexing is that the the time axis is shared among all the channels. So there is specific slot for one particular channel. It was also the case for the analog time division multiplexing, but there we used some modulation, that is pulsed amplitude modulation. So during the on time period, actually the analog data is transmitted. Analog data for one channel is transmitted. Okay, so but in the case of digital time division multiplexing, first the data is converted into digital signal. Analog data is whatever the data, it should be in digital form. So that means sequence of 1010 like that. But in case of analog time division multiplexing, we send the data after sampling of one particular analog signal, and we use one specific slot, and that slot is considered from the clock signal. That slot is taken from the clock signal. We have discussed, we have seen that one first clock is for first channel, second clock cycle is for second channel, third for third one, like that. And again, when all the channels is completed, then again the first channel appears, or again the channels are transmitted in the same sequence. But in digital time division multiplexing, generally data is transmitted through frames. Okay. So one frame actually consists of several channels, and there are the slots are specified for all these channels. So here some difference is that we transmit only the digital data in case of digital TDM, and apart from that, each frame is started with some marker settings. So one markers, so all the frames are generally allotted one channel, that is for marker. So markers are used to distinguish two frames, because there are when the data is transmitted through some medium or from one point to another point, so there are digital data that are coming, and they are coming in sequence of 1010. So how to distinguish this sequence? So the receiver cannot understand whether a new frame has arrived or not. So to distinguish two consecutive frames, each marker is assigned with each frame is assigned with some marker at the beginning of the frame. So and marker is also marker of occupies one channel also. Okay. So you see that it is written that we have used 8-channel digital multiplexer at the transmission end. One channel is reserved for marker transmission, 2 channels for voice transmission, and 5 channels take their inputs from 5 data switches. And each channel has a data rate of 64 kbps. That I will show how it is coming. Now I will show the it. Is the kit visible?
Yes, sir.
Okay. Now you see that there are markers, okay? And generally this is one multiplexer. The multiplexer are well used in case for are widely used for time division multiplexing. So uh, you see that this is the channel for marker, one channel. Total there are 8 numbers of channel. 1, 2, 3, 4, 5, 6, 7, 8. 8 number of channels. And first channel is given for marker. And you see this is the markers settings. Very small switch. Micro switches are used, and here one switch SW1 and another switch SW2. With the combination of these two switches, one marker setting is achieved. So this switch is actually on-off kind of switch. So if you make it off, then 0. Then you make it on, it is 1. So it is, and how there are certain number of bits. Here it is 8 number of bits. 1, 2, 3, 4, 5, 6, 7, 8. 8 bits are there, and in each in these two switches, and combination of these, that is my XOR gate is provided. Okay, so XOR of these two, you can it is used, and one marker setting of 8 bit is generated. This goes to multiplexer input 1. Then there are 5 channels. You see data switches, on and off switches. These are also marker switch. Okay? On and off switch. So when you trace one switch, then 8 number of bits are transmitted. 8 1 are generated. Okay? All are 1. Then another switch, again 8 number of ones are generated. So by pressing certain key, the data can be generated, and so 5 number of data switches are there, okay? And 2 are used for voice channel. You can use receiver. Okay, receiver we are not connected. It's the receiver port. Okay, so you can use 2 landline receivers set here. Handset 1, handset 2. So data from 2 user or voice from 2 user can be transmitted using these 2. Then they are multiplexed, okay, and certain coding scheme, that is Manchester coding, is applied here. That is additional one, that is provided inbuilt the kit, and certain clock frequencies there. There is big role in the clock, and it determines so many um, data rate, okay, and clock. Now here we will show the data, what type of data is present there, and after that see the connection. This is the Manchester coded data. So once the multiplexed once the signal is multiplexed, okay, they are passed through Manchester coding circuit. That is additional thing. Manchester coding you may use, may not use, that is separate issue. That is not the part of multiplexing scheme, but here they are provided. Then after that, the data is transmitted to the transmitter circuit. So it is transmitted in, okay, and after that it goes to the fiber, optical fiber. This is transmitter this is switch, this is LED, okay, and this is the optical fiber. So this is the optical fiber. You can see they have connected, and after that they goes to the receiver circuit, and where we get receiver photo detector, light falls within that, and then we get the output, and received data is converted into electrical form using photo detectors, and then Manchester coded decoding should be applied here. Manchester decoding block is there, and then it should go to demultiplexer, demultiplexer stage. After that, you can see the individual data from individual channel. This is the whole experimental setup. So it is also mentioned in the manual. So you can see in the manual that two switches data, the marker settings is achieved by data from two switches, and you see that the marker setting for transmitter and receiver must be same, otherwise it cannot distinguish, otherwise it cannot match. So receiver should have also the same marker setting, so that when it will compare its own marker settings with the incoming data frame, then it will understand that it is starting of a frame. So receiver also match the incoming data with its incoming marker settings or data settings with its marker. If it is matched, then it will understand that it is a starting of a frame. A new frame has arrived. Then the same circuit description is given in this manual. Okay, you should draw this experimental setup for time division multiplexing. Okay, so it goes through the data, that is multiplex data. Further, it is Manchester coded and transmitted through optical fiber cable, and this goes to detector, and after that goes to the receiver, and Manchester decoded, and again demultiplexed, and further we get the signal from each data, each channel. So this is the process how this is collected, and you see that procedure is written in the manual, and the same thing it is uploaded, the that thing. Okay. So now we'll show we can see here that marker setting table is used. There are two marker setting, they are combined using XOR gate. So this thing is considered here, and now this is the data. So that will observe here. So transmitted data and received data will observe, and first we'll distinguish the frame, how the frames are, what is the data within a chat or after transmission. Okay. Now I'll and you see that there is a pin that is called data UC. So data means multiplex data. It can be seen from, it can be taken from this point, multiplex data, and we have connected through two oscilloscopes. Okay, so one is analog oscilloscope CRO, another is digital oscilloscope. It is better to, in this case, it is better to observe the analog CRO because that does not see the screen. You can see that now suppose if you transmit, okay, one data, that is data from one channel. So I will press this switch. Okay. Individually, I will one by one will press the switch and you will see what is the change is there in the transmitted signal. Let us, so first before pressing the switch, you just see the waveform. Okay. This is actually the marker settings. So all kind of waveform is coming, but still you can see this slot is empty. Okay, and another marker setting is coming. Slot is empty, another marker setting, and this slot is empty, another marker setting. So this way, this is the actual transmitted multiplex signal when no data is transmitted. Now, if you transmit data, what change is there? I will show you. So I will first press this key. Okay. Now you see there's change. So I have pressed data. I have pressed one switch, and data correspondingly transmitted correspondingly changed. So are you able to see it? Just see the change. Now I am pressing the switch on and off. So that data will come or vanish. Data will come or vanish like that. Are you able to see this? Yes or no? Anybody please respond?
Yes, sir.
This is the data when I press the first key. Then second key I will press. Now you see the change. The second key. There is some trace. Can avoid this first. You see here. Then third key. Better you can see here this way. Second data, third data, like that. And again another key. So the empty slots is actually, you see there is change in the data. One by one I am pressing the key, you can see the change in the data. So the next step is you have to period. Okay. So how will measure the frame period? So now I have traced the first data from the first channel. I have given the data, and at that time um, I am showing the waveform. Okay, so there you see that there are frames that are repeated. Okay, so some data is there initially. After that, there is empty slot. Then again, some small fluctuation of data. So that actually corresponds to starting and ending of a frame. Okay, so you can calculate the distance. Okay, time distance between these two data. When one channel is pressed, at that time you measure the time difference. Okay. So you can see this point is actually now you see that from this point to that is starting of this data to starting of this data. This actually give you the duration of a frame. So let me calculate this. So now it is connected to 0.1. Okay, so zero point 0.1 into is 0.5, 1, 2, 5, 10, 20, 15. Okay, then 0.1. So 0.1 goes up to 1, 2. 0.1 is my millisecond is the distance. Okay. Now it goes from 1, 2, 3, 4. So almost it is 4.4 milliseconds. So 0.4 millisecond is the time duration of a no, not 0.4 duration. It is actually up to log 50. Okay, so let me do this way. So here it is actually starting, then it is ending near about here. So 50 plus now it is 50. It is connected to 50. The time division to 50 microsecond. Okay, this one, and this is starting of that data. So and this is the starting of the same data, but in the other frame. This is the data in one frame. This is the data the other frame. So if you measure this distance from this point to this point, okay, what is the distance? You see it is near about 50 plus 50, 100, and it is almost at the middle. That means 25. So 125 microsecond is the frame period. Okay. So 125 microsecond is the frame period, or after 125 microsecond each data is repeated. Okay, so that means sampling frequency is how much? That is, data is sampled at which frequency, or data is transmitted at which frequency. Data from one channel is transmitted at which frequency? Anybody please tell? The same data is transmitted to all the frames, and we have calculated the time distance between two data from two frames. What is the time the time distance? We have got 125 microseconds. What is the frequency? What is the frequency? Please respond. Harshvardhan? Shashwat? Are you listening?
Yes, sir.
What is the frequency?
1 divided by 125.
Yes, 1 divided by 125 microsecond, that is 8 kilohertz. And you know that 8 kilohertz is chosen because of some reason. That reason is it is the sampling frequency 8 kilohertz. That means original frequency is or message signal frequency should be 4 kilohertz. And that is actually the voice signal. Signal maximum frequency is 4 kilohertz considered. We talk generally in 3 to 4 kilohertz frequency. 3 to 4 kilohertz. Maximum voice frequency we consider that is 4 kilohertz. Okay, so that's why sampling frequency should be 4 into 2, 8 kilohertz. So that means one data of one particular channel should be repeated after 1 by 8 kilohertz time duration, that is 125 microseconds. So that is the concept of frame. So frame period should be 8 kilohertz. So there is separate clock. Okay, you can see in the diagram. So there are different clocks are arranged. This is the clocks for frame period, that is 8 kilohertz. This is the transmitted data. Okay, and these are the markers. Okay, and this is actually slightly random. Okay, but generally there is some many waveform are superimposed, you can say. That's why it is slightly get elongated. And another data, so another data is calculated, that is the data rate. Okay, data rate is 64 kilohertz. How we calculate the data rate? That is given in the next part of the experiment, that is study of framing. So you can see here that 125 microsecond is provided for 8 number of channels. So 125 divided by 8, okay, is a certain value, and if you reciprocate it, take the reciprocal, that is 1 by this thing, or 8 by 125 microsecond. So each channel is you can calculate the channel duration. That means time allotted for one particular channel. Okay. So anybody please calculate what is the value of 125 divided by 8. What is the value of 125 divided by 8?
15.6.
15.6. So now this is the microsecond. Okay, so you just make 1 by 15.6. Okay, so how much it is? 1 by 15.6.
64 kilo.
Yes, 64 kilos. So there is another clock needed. Okay, that is the multiplexer clock. Okay, that is given. So multiplexer clock means it assigns the time durations for one particular channel, and it assigns for this 15.6 microsecond for each channel, and that corresponds to 64 kilohertz. So this is another clock needed for multiplexer. Okay, that it it provides actually certain time duration for each and individual channel, that is 64 kilohertz. Then also transmitted data clock, that is 512 kilohertz. Okay, 512 kilohertz is calculated, and this is calculated this way. So you see, study the last line, that since we transmit 8 bits of data per channel, 8 bits per data per channel, so it is actually the channel data rate can be achieved as 15.625 divided by 8. So again, this is divided by 8. So total frame duration is 125 microsecond. In one frame, 8 channels are transmitted. So one channel duration is 15.625 microsecond. And in this 15.6 microsecond, 8 bits are transmitted. That means for one bit, we get the time duration as 1.9, almost this frequency, one time period, and divide by it, 1 by, if you just calculate 1 by 1.9, it becomes 512 kilohertz. So this is the actually data rate. Data means how many bits are transmitted per second. So that you can calculate by dividing the total time durations, the total time duration divided by number of bits. So 8 channel, 8 into 8, and each channel 8 bits, so 8 into 8 is 64. So 125 by 64 is the bit time allotted for one bit. So this way it is calculated, okay, the frames, and so for that again another clock is required, that is given here. Okay, I am not showing you in the kit. There are different points. You can observe this waveform. You can observe this data. Okay. These frequencies you can see here. There is provision of select yes. 64 kilohertz, you can see here 64 kilohertz, 32 kilohertz. It is up to you that what frequency you should choose. So based on this and based on the jumper settings, Jumper settings you have to use this way. So you have to perform the experiment, and also you have to study the manual, okay, thoroughly. And if you have any doubt, you can ask me. And you just make the lab journal according to the things that are given in the manual. Okay. So anything you want to know? Have you understood it? How to calculate the frame period? From the CRO? Have you understood? Ashank,
Yes, sir.
have you understood?
Yes, sir. So the graphs, can you just show them again? The output waveform.
Okay. You see that when one by one I press the key, and generally data is transmitted to the frames. So suppose if I press one key, okay, here one key, okay, then you see that this data is generated and transmitted. And second key, data is generated and transmitted. So if you measure the time difference between that two data, okay, there is very small, its visibility is not that much, but if you are present here, then you can see it. Yes, now you can see that once I press the data, You see the change is here, this point. Now this data is coming here. Now the same data is here, but at the other frame. Now you have to calculate the time, this difference, time difference between this data to this data. This data to these two data are same, that is sample one. Okay, so if you measure the duration of this time difference between these two, then you can measure the frame period, because they are situated exactly with a time difference, time duration of one frame. One sitting is one frame, another sitting is other frame. Another data in another this thing you will see. So this way it is calculated, and that is coming to be 125 microsecond. Now again I am showing you now. This is one data. Okay. We just okay. I have enlarged it. Okay. Once I press, so this is one frame. From here to here one frame, and from here to there another frame. So if I press one data, then data is going in this frame and to the next frame. So if you measure the time difference between this point and this point, this will be exactly equal to what? This will be exactly equal to the frame width, isn't it?
Yes, sir.
That is, we have got 125 microseconds. You can measure the time duration between two markers also, this point to that point. That will also come 125 microseconds. Then another data, another same another signal. Okay, then another. The slots are fixed. Okay, slots for all these channels are fixed. Anything else? Now I will show another thing in the digital CRO. Okay. So here you see that several frames are transmitted, and these are the frames, and these are the I am just adjusting the CRO. that it would be here. Now suppose these are the markers. Okay, you can see some beats are there. Now if I change the marker beat, okay, there you can see the change. Do you see the change? Now you see I'm changing the marker bits here, and you can see the change. Do you see the change?
Yes, sir.
Anyhow, when you will come here, you should must see the experiment. Okay, then stopping here. May leave now.